In the CfA Seminar. It is my pleasure to introduce our first speaker of the day, Daichi Tsuna from Caltech. He got a PhD from University of Tokyo in 2022, and then he moved to Caltech as a Berkeley Fellow. That's where he is now. And then he's an expert in like massive star evolution and then how they lose their mass in mysterious way in the final decades or so. That is, what everyone is wondering about. And then he's going to tell us the answer today. So, yeah. The floor is yours.
Yeah, thank you for inviting me, and is the mic not turn on? Test. Maybe I should put it closer. That's right. So thanks for inviting me, and it's a pleasure to be here. Pleasure to meet a lot of people. I'll be around till Thursday, so I'm very excited to see everyone working on transients and everyone not. So today I'm going to talk about where the mysterious phenomena called supernova precursors that has been found over the past decade or so, and it's a very mysterious transient that we would really want to know what is the origin. Okay, so the main topic here is about what's called a class of supernova called type 2n or 1bn. And N stands for narrow lines. I think many people in the room already know what people think is causing these narrow lines. So what the consensus pretty much emerged so far is that this supernova progenitor that is about to explode has a very slow and dense circumstellar matter around. And when the supernova explodes, the ejecta hits this slow dense CSM, creates a shocked region that produces a lot of photons. The photons, when they escape to infinity, they get reprocessed, partially reprocessed in this dense CSM, manifesting as a narrow line in the spectra. And based on this model and the time scale to see these narrow lines, the density required, what people find is something extraordinary happening in the last months or years before core collapse. And this months to years is basically only like the last 1/1,000,000th of its life. And something weird is happening in this final moments of its life. So this was not really predicted in conventional stellar evolution theory, and people want to know what is causing this. Well, how will we know? And one probe is to actually see what is creating this dense CSM. That's probably one promising possibility. And we have a similar analog of this in our galaxy, the ETAC arena, which basically ejected like solar masses of material at around the year 1800. And then this star basically brightened by like a few magnitude, and then dim due to dust formation. So do we actually see this kind of phenomena in these like interacting type 2n 1bn supernovae? And turns out that we do. So now the terminology is called supernova precursors. They seem to be quite commonly happening in these type 2n 1bn supernovae. So this is a sample by ZTF people. So basically, they selected a sample of type 2n 1bn supernovae. They looked at the archival data from the ZTF, and what they find is these kind of optical flares occurring from like months to years before core collapse. So turns out this is quite common in the sense that roughly a quarter, well, with an error uncertainty of like factor 3 in both sides, but due to small samples, but roughly like a non-negligible fraction of 2n's, and roughly 10% of 1bn seems to have these kind of bright precursors, and their search is basically magnitude limited, so they only look at the brightest events, of course, but the brightest events tend to have less than -13 mag, which is at least 10 times the Eddington luminosity of massive stars. So, and then for the very luminous ones, the radiated energy becomes like 10 to the 40, 49, which is much greater than the binding energy of hydrogen-rich supergiants, which is like order 10 to the 47. So if you want to power this emission, one way is maybe you will blow up the whole star. But then you wouldn't see the supernova. So something's wrong here. But maybe this energy can be just channeled into the hydrogen-rich envelope, eject the whole envelope. Would that be possible? It doesn't seem to work so much in practice. And the reasoning here is that, so the supernova 2N with precursors and those without like a detected precursor, there might be one, but which aren't bright enough to be detected. When we look at the luminosity of the supernova, so the after the precursor, they seem to be similar in brightness. So the model of like ejecting the whole envelope wouldn't work because that's presumably going to create much stronger interaction and a much brighter supernova, which we don't see. So the solution has to be somewhere that doesn't involve like the energetics of the eruption itself. So how do we do this? So we came up with one model where we consider stars in a binary system with a compact object. So in our scenario, basically, the ones that don't have bright precursors might be the ones that don't have a compact object companion. And the ones that are bright might be the ones they do. And originally, this star and the compact object is not interacting. The star isn't filling its Roche lobe. Let's say there's some mass ejection event that creates a dense CSM. So one possibility is like these pre-supernova outburst mechanisms people have been talking about over the past decade or so. And initially, the CSM will just be expanding. But at some point, part of the CSM would be captured by the black hole's Boundary radius. And when that happens, when the separation is like not so far, the accretion onto the black hole, estimated by the Boundary rate, is going to be much bigger than Eddington accretion. So what people have found from simulations, including I think people in Harvard, have found that these super-Eddington accretion tends to source powerful wind outflows. So basically, the energy of this precursor, what we propose, comes from this accretion energy power and the outflow that is powered. So based on this model, based on this toy model, we can try to build what the precursor emission would be, how bright it is, and how long it would be. And to do so, we created a one-zone model of this wind-heated CSM. So, sorry, I'm going to come back. But so this CSM would be heated by this wind that is coming out from this accretion onto the compact object. And we basically build an equation to characterize the thermodynamics of this CSM. And yeah, this is the only equation that's going to come in this talk. So I hope you bear with me. So the internal energy change is basically the PdV work, the expansion giving the internal energy into kinetic energy, and the injection by this disk wind. And we make some assumptions here on how we model the disk wind is basically we measure how much of the CSM would be captured within the Boundary radius of this compact object. It can be a neutron star, it can be a black hole. The Boundary radius would change in either case. And then we model the classical way of how people model the wind outflow from this radius inefficient accretion flow. And then what we're mostly interested in is basically what comes out as radiation. So this is evaluated as basically the internal energy divided by the diffusion time. So diffusion time can be estimated by the mass and radius of the CSM for a one-zone model. And we assume a constant opacity, but include recombination effects as how people model in type 2p supernovae light curves. So with this equation in hand, the key parameters are basically, of course, the mass of the black hole, neutron star, and the mass of the star, radius of the star, which controls the velocity of this CSM. But I guess those are relatively fixed given if you assume some kind of progenitor. And what is more subject to change from one binary to the next is basically how much CSM would be ejected and what is the orbital separation of this binary. So as you can imagine, binaries that are farther out would accrete less of material, so you would end up with a dimmer precursor emission. So what we did is basically vary these kind of parameters to see what are the precursor emissions that we get. So I'm going to show an example for a couple cases, focusing on the case where the star is a tensile mass red supergiant that is about to explode. So red supergiants are the most common endpoint of massive stars when they right before they die as supernovae. So it's probably a good star to start with. And we consider a tensile mass black hole companion. So when the star ejects the CSM, there will be emission from that mass ejection event. But those will be much dimmer. So you can see the light curve luminosity, sorry if it's too hard to see, but it's about 10 to the 39 at peak. And that's less than the Eddington luminosity. But once the CSM expands and reaches the compact object, there's going to be an accretion injection in luminosity by the wind, which basically makes the emission brighten again. And the peak luminosity can go much brighter than the initial eruption, which is like 10 to the 41, 42. And you can see the parameter dependence, which I alluded a little bit before. So the larger separation means the CSM takes a longer time to reach to the compact object. And also your CSM being accreted is going to be much lower mass. So if you compare, for instance, the blue line and the orange line, which is just changing the separation, you can see that the light curve starts later and it's dimmer. The effect of raising the CSM mass is a little more subtle. When you fix the separation, you accrete more mass, but your diffusion time is going to be longer because your CSM is more optically thick. So you can have like a somewhat longer and somewhat brighter light curve. Okay, so yeah, that's it. So we can compare with the observation of these precursors. I've selected a subset that has a well-sampled light curve. And I think, so the filled dots are basically the precursor emission. And we distinguish it as empty dots as emission where we think the supernova has happened and afterward is supernova. So we're not like perfectly fitting the light curve, but at least the luminosity and the time scale seems to be a pretty good match, and we're probably doing a pretty good job on reproducing the light curve. So besides the light curve, our model can have another byproduct, which is because we model the acceleration of the CSM by PDB work, we can get the velocity as a function of time. So if you have the companion much farther out, you're going to have much less accretion energy, so you can't accelerate the CSM much. But for the cases where the precursor is brighter, you can have much more energy injection. And that actually accelerates the CSM velocity to like from 100 to 1,000 kilometers per second, even for a red supergiant progenitor. So, and the observed CSM velocity of 2n is roughly 100 to 1,000 kilometers per second. So maybe this can create a diversity in this velocity, which is just a speculation, which might be able to confirm if we observe more precursors of these. So We can do a little more of a parameter study to see how the luminosity and duration depends on the mass of the CSM and the separation. As I alluded before, the separation, when the separation is wider, it becomes dimmer and lasts longer. So what we predict for the red supergiant model is basically a broad range of luminosity. So it can have like, the dimmest can be like 10 to 38, which is like almost the luminosity of the star itself, the red supergiant itself, to 10 to 42, which is like almost close to a supernova. The time scale can go months to year. This, of course, depends on the mass of the CSM you vary, but for the CSM mass you typically see in type 2n, it's roughly months to a year. And one thing we can infer from this is that, so when we compare with the observed precursors that are well sampled, we do a pretty good job in reproducing these, especially for the case when the companion is a black hole. But what we can also see is that there are a lot of predicted low luminosity precursors that we haven't really observed, likely because this precursor search is magnitude limited at this point. So we probably need much more sensitive surveys in order to detect these low luminosity precursors if there are one. So I think Rubin is going to be very important to detect these kind of low luminosity precursors. So I showed the plot for the red supergiant. We can similarly do something for a helium star companion. So in this helium star case, the star is more compact. So you're going to consider a much more compact binary rather than like a 1,000 solar mass, solar radii separation binary for red supergiants. So the time scale, the whole precursor emission would evolve much faster than red supergiant models. And the time scale would be from days to about a month or so. And these two are the observed precursors at this time of the paper. This paper was written. The wide variation in luminosity, and also for helium star models, they enable us to reproduce the emission of the precursor that we see. The four models basically change. The helium star has a much bigger parameter space in terms of radius because low mass helium stars inflate a lot compared to high mass helium stars. So there's a little bit of diversity in what the progenitor we expect. Yeah, but similarly to the red supergiant case, we predict there's a lot of dimmer precursors that we just haven't really detected. And I guess Rubin would be important to search for these. So I'm going to conclude with a couple implications of our model. So we consider a binary system. So one might think, how can we link to the binaries that we have already found? So one of them is the black hole binaries recently detected by Gaia. So for our red supergiant models, which we claim to reproduce the 2n precursors, so those have periods of roughly years in order to reproduce the bright emission from the precursor. So if we go back in time, when the red supergiant was still in the main sequence phase, we probably think the orbital period hasn't evolved that much from when it is at this point. So the main sequence star and black hole neutron star binaries, they might be observable as Gaia sources in the Milky Way. So Gaia is an astrometric satellite that basically looks for astrometric wobbles of stars. And so far they have found a black hole neutron star, or black hole or neutron star, and typically a 1 solar mass star binary. There's a lot of findings by Kareem, who is here, and now he's in Caltech. In the future, we might be able to find these like massive star compact object binaries, which can become a good test of our model. The second one is potential link to future gravitational wave sources. So this is the case for a helium star. So helium stars can have radius down to like a solar radii. And when they have, well, a compact object companion, when the helium star explodes, there will be a kick, of course. So the final separation when the helium star becomes a neutron star wouldn't like completely be the same. But if we have tight enough binary, the final neutron star black hole binary would be able to emerge by gravitational waves within the Hubble time. So there are rate estimates for black hole neutron star binaries, which is about 100 per gigaparsec cubic per year, which I think is a coincidence at this point, but matches with the observed precursor rate of supernova 1BN. So, I mean, we probably should try to wait for the future to try to constrain these rates even further. I think we can do that. But these point to an interesting link that like we might be able to further consider, for instance, by population synthesis models or other ways. Okay, so I'm going to conclude here since I'm running out of time. So yeah, the observed precursors of 2N and 1BN, they're very bright, and we have considered a model where it's a compact object companion that is powering the emission. And I guess the key take-home message I would want to say is that we're probably going to find a lot more precursors in the Rubin era. So Alex has done a very nice analysis of prediction of how many precursors we will find in Rubin, probably hundreds per year. And maybe we can find the dimmer ones that current optical surveys have missed. And final thing to know is we have our light curve model as a public Python code. So in case you find a bunch of precursors, this might be one way to test. Okay, thank you.
Questions?
Yeah, I've got a couple of things. One is you were predicting not only the luminosity and the duration, but also the velocity.
Yes.
So have you looked at the 3D space and to see if that's very constrained? It might be a more stringent test.
We haven't looked into this simply because we don't have that many samples of these well-sampled precursors and the velocity.
It could be a prediction.
Yeah, I think it would be good to predict. We haven't really done that, but yeah, that's a good point.
And so, as an exoastronomer, I always say you see a neutron star, black hole, where are the X-rays? I assume that at first they're going to be completely swamped by the quantum-thick atmosphere, but at some point is there a breakout?
Yeah, that can happen if the CSM had expanded large enough. But the accretion rate would also drop as a function of time, so we have to be a little careful on the detectability. And yeah, so the accretion itself, if it's limited by, like, for instance, the Eddington luminosity, then I think we can't really detect that far with like current. Maybe Chandra can detect up to like tens of megaparsec, but these are probably like 100-ish megaparsec or more, quite far.
Other questions?
Yeah.
So I think something really interesting here is that you're thinking kind of about a discrete chunk of CSM, for lack of a better word. It's like 0.1 solar masses or something like that, and it's lost in an instant. And I don't know, what if a star has a certain mass loss history leading up to the supernova? How does that change things? How does it matter if that CSM has some profile? Like, does that go into changing the shape of this light curve, or does it change the dynamics in some?
I think it would change both. We assume basically, so when we model the history of this accretion, we basically assume the CSM is homologously expanding and with a uniform density profile. So that's an assumption.
Yeah.
If we change that assumption, the light curve morphology would probably change a bit.
Yeah.
I think the bulk like timescale luminosity would be preserved.
Yeah. Super interesting.
Yeah, and we did consider about mass transfer scenarios, and I didn't have time to go
No,
songs, but we can talk later. Yeah.
Definitely.
Yeah.
Other questions?
So, from the optical observing side of things, I have two questions. What do the spectra of these things look like? And because these seem to be very asymmetric systems,
Yeah.
is there a way, hypothetically, if we got a spectrum early enough, is there a way to confirm this scenario from the spectrum, taking into account the asymmetries? And I can just ask a second question as well. During Rubin, we're going to find a lot of these objects, as was shown. What would be the smoking gun signature of these interactions? For example, if we got very high cadence photometry, do you expect to see some type of periodicity as these two objects are orbiting each other?
Yeah,
For example.
I think that's a really important point to pursue. I think the periodicity is quite long. Like it depends on the system, of course, but for like a retrospective periodicity is like years, so
Sure.
it'll probably be hard to find them. The more tighter objects, it might be possible to have like the orbital modulation. But I think it might be smeared out by the diffusion in the ejecta. But I agree there can be some spectral imprints in the symmetry. I think you found something like that for like the 2023 FIQ.
Sure,
Yeah.
but in relation to FYQ, I was wondering, could this, obviously you did show that this scenario does fit FYQ, but I wonder, is there a way to confirm that
Yeah.
spectra? But
Yeah.
that's a very open-ended.
Yeah, I think we need to do multi-dimensional simulations, and yeah, that's future work.
Can I ask one more? Sorry. So, in a sense, the supernova itself isn't too different from that precursor mass loss episode in that the star explodes and maybe it has a homologous velocity distribution and it goes by the compact object. So, is there a situation where like the low velocity tail of that material could like re-energize the late time light curve? Like the fact that there's a potentially accreting compact object in the middle, is that an energy source at late times?
Yeah,
Prediction of this?
it might be possible. I mean, it depends on the velocity profile of the ejecta.
Yeah,
if it's
of
like a
course.
slow component, then yeah, it might fall back. I think there were scenarios by Damir Labati and others about like companion accreting the slow tail of the ejecta. Yeah, it'd be good to look into that. We didn't.
In a sense, you might capture some of the mechanical power in the same way where you have like fast disk wind interacting with the supernova ejecta in that case. And so you wouldn't necessarily be like limited to the thermal emission.
Yeah, that can make the supernova brighter then.
Yeah.
But like the interaction makes it already quite bright, so
Yes.
it's a little hard to,
It's a
hard to
bar
find
to match.
find the smoking gun of this.
Okay.
Yeah.
Maybe one more last question? Okay.
Can I go again?
Oh, yeah, sure.
The light curves on the left-hand side, a lot of them show the pre-peak bumps in the light curve.
Bumps.
For example, with ZRK, you have a bump at late times. And over to the right, yeah, these bits. Can you link that back to your...
Oh. That's an interesting point. I think this like binary process might make some like inhomogeneity in the CSM profile. I mean, we assumed it to be the one of those slabs, so like we can't really predict it from our model. But I think that also needs like a simulation to actually see the profile.
Yeah. These
But
ones are very common. In all two ends, that post-peak bump is quite common, so
Yeah,
it'd
and
be interesting to explore that.
the asymmetry might play a role in that.
Sure.
I agree.
All right. Let's thank Daichi again.
I think we might talk there. I'm so excited by your work. It's just so cool.
Yes, still turn on.
So I think we have a meeting planned for, with Ashley
want to do those kind of analysis and
Yeah.
see like from the precursor to the supernova, how it works. I mean, it's based on our model.
Sure.
But yeah, no, would be good to explore. Yeah.
Absolutely. We'll talk more about this tomorrow.
All right, we'll move on to our second speaker. So I'm very happy to welcome Zach Fried today. Zach obtained his bachelor's from Macalester College in 2021, and he's now a graduate student in the McGuire Astrochemistry Group at the MIT Department of Chemistry. Zach's work combines machine learning analysis of complex chemical inventories with both laboratory spectroscopy and observational radio astronomy of astrochemically important molecules. And his talk today will be about the chemistry of some newly detected complex oxygen-bearing molecules in a massive protostellar cluster. Go ahead, Zach.
Yeah. Hi, everyone. Thanks for having me out today, and thanks for the introduction, Brian. So today I'm really excited to present some recent work I've done on measuring the rotational spectrum of 2-methoxyethanol leading to the first interstellar detection of this molecule toward NGC 6334I. And I apologize if this slide is a little bit simple, but even for an astronomy or an astrophysics audience, astrochem can be a bit more of a niche subfield. So it's useful just to talk through what astrochemistry really is. So for me, I like to think of astrochemistry as just the study of molecules in space. First of all, where they are, so using radio telescopes to detect which molecules are present in different interstellar sources. Second of all, how they got there, so understanding the specific chemical reactions that are forming these molecules, and finally what they're doing. So which reactions these molecules are actively involved in to continue to build up molecular complexity in space. And really the backbone of this process, if we want to understand the chemistry that's occurring in the interstellar medium, we first just need to detect new molecules in space. So this list right here is a little bit outdated, but as of January of this year, there had been about 300 molecules detected in the interstellar medium. This number is up over 320 now, but there's just a couple of things to point out here. First of all, the vast majority of these molecules are really quite small, especially for terrestrial standards, having 8 or less atoms. In fact, as of January, this number has gone up a little bit now, but as of January, there were only 11 molecules with 13 or more atoms that had been detected in the interstellar medium. And there's a couple of pretty practical reasons that we've detected so few of these large molecules. First of all, and this isn't always the case, but generally, larger molecules are just less abundant than their smaller molecular counterparts. And if a molecule is less abundant, its spectroscopic signature is going to be weaker, and therefore it's going to be harder to detect in our radioastronomical observations. So just to sort of show this in action, here I've plotted the column densities of several cyanopolyions toward the TMC1 cold dark cloud, ranging from HC3N up to HC11N. And you can see for every increase in chemical complexity as we go to larger and larger molecules, the column density will decrease. But just to show why this matters, here I've simulated the rotational spectrum of HC5N at the column density that we've detected this molecule with toward TMC1. And on this figure, the red line is the general upper bound of our noise level toward our observations toward TMC1. You can see in this case, if HC5N is present to this large column density, all of the lines are going to be super strong above the noise. Detecting this molecule is really going to be a piece of cake. However, if we take the same spectrum and simulate it with the column density that we detect HC11N at, well, the lines pretty much disappear. Now, we can zoom in on the noise level, and maybe there'd be a couple of lines just peaking above the noise, but ultimately, if you're trying to detect molecules based on seeing individual lines above the noise, it would make it really challenging with this abundance. To sort of compound this issue as well, not only are larger molecules just less abundant, but they oftentimes have more complex spectroscopic signatures as well. So not to get too deep into the weeds, but just because of the quantum mechanical fundamentals of rotational spectroscopy, larger molecules generally have more narrowly spaced rotational transitions. So if you have the same population of 2 molecules, and the signal of one is spread out over a greater number of transitions, well, each of those transitions will therefore be weaker. So here we've simulated the rotational spectrum of HC3N and HC7N with the same column density. And you can see over this frequency range, HC3N has far fewer transitions, but each one is much stronger, making it therefore easier to observe above the noise in our observations. So far, I've been talking mainly about cyanopolyions toward TMC1. And TMC1 is this cold, dark molecular cloud that's prior to a star actually forming. And this source is really the main source of interest for our research group, along with our Gotham collaboration, which the McCarthy group here at the CFA is really an integral part of. But more personally, during my PhD, I've been interested in sources in which a star is actually forming. So these warmer, more turbulent star-forming regions. And that leads to the question, well, why do we even care about molecules in these star-forming regions of space? Well, with every new and larger molecule that we detect, we could sort of start to unravel how efficiently molecular complexity can develop in these very harsh conditions surrounding forming stars. Additionally, by comparing the molecular inventories of these star-forming regions to preceding molecular cloud sources, we can kind of answer the question to what extent the chemical inventories of these star-forming regions are actually just inherited from previous steps along the star formation process. And oftentimes what we see is that these smaller, simpler hydrocarbons, things like acetonitrile or methanol, may be detected in both of these sources. However, these long-chain unsaturated species we've only really observed in these cold molecular clouds. So if that's the case, what sort of molecules are we generally seeing in our astronomical observations toward these star-forming regions? And oftentimes, these molecular inventories are dominated by these very oxygenated and oftentimes quite saturated hydrocarbons. But if we look a little bit closer at some of these small subset of examples, you can see that one very specific chemical motif that shows up over and over again is the presence of this CH3O, this methoxy group. In fact, there have been 5 different methoxylated molecules detected in these star-forming regions, namely dimethyl ether, methyl formate, methyl acetate, ethyl methyl ether, and methoxymethanol. In fact, dimethyl ether and methyl formate were actually some of the earlier complex organic molecules detected in the interstellar medium. So with this in mind, knowing that we've detected so many of these methoxylated species, we thought it was a good idea to continue looking for molecules within this chemical family. And at the time we started this project, the methoxylated versions of methane, methanol, and ethane had all been detected. So a really straightforward next step is therefore to look for the methoxylated version of ethanol, namely a 13-atom molecule called 2-methoxyethanol. If we want to detect this molecule, we first of all need to measure its rotational spectrum, because this is the signal that we observe in our radioastronomical data. And if we went to the literature, we'd see that there were 2 previous rotational studies of methoxyethanol. First of all, in 1972, Buckley and Brochu measured the 8 to 26.5 gigahertz spectrum. And then in 1986, Caminati et al. Followed up and extended the spectrum up to 40 gigahertz, measuring some higher quantum number transitions as well. And while this is a really, really useful starting point, if we want to detect this molecule in the star-forming regions in which we're interested, which typically range up to several hundred Kelvin, we first need to measure the higher frequency data. And just to show the reason for this, here I've simulated the rotational spectrum of methoxyethanol, first of all, at 10 Kelvin, so a temperature much more relevant to a molecular cloud like TMC1, and then 300 Kelvin, which is much more relevant to a star-forming region. You can see at 10 Kelvin, the strongest transitions fall between maybe 50 and 100 gigahertz, whereas at 300 kelvins, the strongest transitions are 200 to 400 gigahertz in the sub-millimeter wave frequency regime. So in order to give us the best opportunity to detect the strongest transitions of this molecule in our data toward these star-forming regions, we need to measure them in the laboratory first. So in order to do this, we've added 3 new spectroscopic experiments of this molecule. First of all, one of our colleagues, who at the time was at the New College of Florida, now working for BrightSpec, Dr. Steve Shipman, remeasured the 8.7 to 26.5 gigahertz spectrum. And you may notice that this frequency range actually overlaps with the previous studies by Buckley and Brochu and Caminati et al. But just with some more modern spectrometers and better fitting methods, we were able to get a bit of a better and more constrained fit in this frequency range. We then continued to study the spectrum up to 68 to 85 gigahertz using a newly developed chirp pulse millimeter wave spectrometer over at MIT. And then finally, the bulk of the new experimental work was done between 150 and 500 gigahertz over at the University of Lille in France, which is where I spent most of November last year collecting the data for this project. And for this, we used their state-of-the-art absorption spectrometer out there. So now that I've talked through the new experiments, we can get to some spectroscopic results. And here in blue, you can see just a small frequency subset of our measured rotational spectrum. And once we measure the spectrum, the first thing we need to do is analyze or fit the spectrum. And in order to do this, we need to assign each line that we see to a specific quantum number transition, put it into our fitting software, which will determine values of rotational and distortion constants and give us this fitted spectrum, which I've simulated here in red. You can see that the fitted spectrum really closely overlaps with the measured spectrum, in this case to even less than the experimental uncertainty. You may also notice that there's quite a few measured lines that actually aren't present or don't line up with transitions in our fitted spectrum. And the reason for this we'll get into right at the end of the talk. But now that we've measured and analyzed the rotational spectrum of this molecule, we can go ahead and search for it in space. And one source that we were particularly interested in was NGC 6334I. So this is a high-mass region of star formation within the molecular cloud complex NGC 6334, otherwise known as the Cat's Paw Nebula, because of its pretty cool appearance. But the reason this was such a good target to search for this molecule was, first of all, it's been studied extensively with ALMA observations, and second of all, it has a very large known molecular inventory that's dominated by these oxygenated and saturated hydrocarbons. In fact, this is one of the two sources in which methoxymethanol has been detected, so just one step lower in molecular complexity than methoxyethanol, therefore making it a good source to search for methoxyethanol as well. So now just to talk through some of the results of our search toward NGC 6334I, and in these figures, the black trace is our observational data toward this star-forming region, and then in magenta, we've simulated the rotational spectrum of this molecule. And generally, if we want to claim a detection of a molecule, we have to observe a certain number of transitions. The relative intensities need to pretty much match what we observe, and there can't be any missing transitions along the way. Now, as we scroll through the frequency coverage of our observations, what you'll see is that all of these criteria are in fact met. In this case, we observed 25 different rotational transitions of methoxyethanol in this source, no missing transitions, so we can very confidently detect this molecule toward NGC 6334I. So that's an exciting result, detecting a new molecule, especially one of the few 13+ atom molecules that's been detected so far. In fact, as of now, this is the largest oxygen-containing molecule that's been detected in the interstellar medium or circumstellar shells. So once we detect this molecule, we can go ahead and determine certain physical parameters for this species, things like temperatures and column densities. And not to get too deep into the details, but in order to do this, we utilized a newly developed automated fitting routine by Dr. Samer El-Abd over at the University of Virginia. And ultimately, through this process, we found that methoxyethanol in this source has a column density of 1.3 times 10 to the 17 inverse centimeters squared. And on its own, this number isn't super interesting, but it can be interesting if you then compare it to the abundances of other similar hydrocarbons. So one interesting point is that methoxyethanol is actually only 12 times less abundant than ethanol in this source. So for astrochemical standards, methoxyethanol really is quite a bit more complex than ethanol. So it's pretty surprising to see it be only 12 times less abundant than ethanol in this source. Additionally, methoxyethanol is 31 times less abundant than methoxymethanol, which is just another interesting gauge of how efficiently we're building up molecular complexity in this source and continuing to add on to these carbon chain species. But as I mentioned at the beginning of the talk, as astrochemists, we don't just want to detect the molecule, even though it's pretty fun to do so, but we also want to understand how these molecules are getting there, which specific chemical reactions are forming these molecular species that we detect. And the first potential family of reactions that could potentially form methoxyethanol are radical-radical recombination reactions that would most likely occur on grain surfaces, and then the products of which would be desorbed into the gas phase once the star begins to heat its surroundings. The first potential reaction is the recombination of CH3O, the methoxy radical, which is a known detected interstellar species, with CH2CH2OH, which through theoretical studies has been shown to exothermically and baryolously form through the addition of the OH radical to C2H4 ethylene. Methoxyethanol could also potentially be formed via the recombination of CH3OCH2 with the hydroxymethyl radical CH2OH. And while neither of these radicals have been previously detected in space, they're both pretty well-studied astrochemically relevant radical precursor species. Now, methoxyethanol could also potentially be formed via these insertion reactions involving singlet-excited oxygen and singlet-excited carbene. So both these singlet-excited fragments are known to form very efficiently through the interaction of astronomically common molecules, things like water, carbon dioxide, and methane, with either UV radiation, cosmic rays, or energetic electrons. And it's been shown via both theory and experiment that these singlet excited fragments can exothermically and barrierlessly insert into the bonds of smaller hydrocarbon species to continue to build up larger molecules. So it should, in theory, be feasible, energetically feasible, for singlet excited oxygen to insert into ethyl methyl ether, or singlet excited carbene into methoxymethanol or ethylene glycol to form methoxyethanol. All three of these precursor suggested molecules are known detected interstellar species. So that's the main bulk of the work we've done so far on this project, but there's still quite a bit of work to do. So as I mentioned a couple slides ago, there were quite a few lines in our measured spectrum that couldn't be accounted for by the rotational spectrum of the ground vibrational state of this molecule. And one of the cool things about rotational spectroscopy is that it provides completely distinct rotational spectra for molecules in different vibrationally excited states. And you can see here, especially in our spectra collected out in Lille, we were able to populate quite a few of these low-lying vibrationally excited states, which we have to go ahead and fit the rotational spectra of now. And we started doing this for the lowest lying vibrationally excited state, which we've simulated here in red over our NGC 6334I observations in blue. And you can see that there is quite a high level of overlap with even some potentially unblended transitions. So while this is a very tentative result, and we still need to continue to shore up our spectroscopic fit and look more into our astronomical data, it is quite promising and suggests that we'll maybe be able to detect these vibrationally excited states of this molecule as well. So with that, I'd like to say thank you for your attention. Thank you to the group shown on the screen. The entire author list is listed along with their affiliations, funding source of Schmidt Family Futures. If you're interested in reading the paper, feel free to scan the QR code. Once again, thank you for your attention. I'd be happy to take any questions you may have.
Any questions? Julie?
Yeah.
Thank you, very interesting. So I understand that for lower J's you get intensity from start measurements. How confident you are in intensity, so ice-snake coefficients of these higher J's that you actually identified in space?
Yeah, so that's a great question. So when we measure the spectrum, the first step is to fit the spectrum, of course. So we don't just rely on the measured relative intensities. But once we fit the spectrum and we get the values of the rotational constants, the distortion constants, and we also understand the partition function, we can really accurately, just through simulation of the spectrum, reproduce correct rotational intensities. So they're very confidently known.
Julie, are you getting at distortion effects to the dipole moment itself?
Yeah.
Ah, okay.
Yeah. Well, yeah, but you basically have relative. But this measurement is in emission, right? Is it? Or it's in absorption?
So the astronomical or the experimental?
The lab.
The lab, it's an absorption spectrum.
It's absorption. Okay.
Yep.
Go ahead.
Yeah.
So you mentioned there are several channels to make the NFDX.
Yeah.
So the external. So can you measure like the abundance of each component so that which channel would dominate?
So yeah, I mean, for all of these molecules, we have of the precursors, we have known abundances of these. But to really understand which of these are contributing most, it takes a lot of both theoretical and experimental work in the laboratory to determine the kinetics and the energetic feasibility. So just the abundance of the starting material isn't really a super useful gauge. It's useful, but it's not like the be-all and end-all for which of these pathways is going to be the most efficient. We need both kinetics and experiment and thermodynamic studies, and then to incorporate these into our astrochemical models to see if we can possibly reproduce the abundance of methoxyethanol with our proposed reaction pathways. Yeah.
Apologies if I missed it, but you have a detection of this molecule. Did you have an abundance as well?
Yep. Here we go. So the column density, about 1.3 times 10 to the 17. We have comparisons here to other similar molecules is all I have on hand, but about 12 times less abundant than ethanol, and then about 31 times less abundant than methoxymethanol, which is one step down.
And it's kind of surprising, this abundance?
Yeah. Just because, as I said, ethanol is a fairly common molecule in these star-forming regions. Methoxyethanol, first detection of quite a large molecule. And it's only 12 times less abundant, which isn't a huge abundance gradient, which is kind of surprising. We also looked in a low-mass star-forming region and we didn't detect methoxyethanol, and in fact, we found that it was at least 92 times less abundant than ethanol. So really different relative abundances in these two sources, which suggests something about the chemistry, which is interesting.
So I have a question on the formations. Can you go back to the O insertion slide you had?
Absolutely.
So on the radical recombination on a grain surface, that's seems it's a reasonable thing.
Yep.
And then so on the O insertion, I guess idea would this would also be occurring on a grain surface.
Exactly.
So is the lifetime of these excited, O singlet is an excited state, singlet methylene is an excited state. Are the lifetimes of those on surfaces long enough to do chemistry, or do those get quenched immediately?
Great question. So the experimental studies have been on surfaces in the labs and gauging very similar reactions, including these oxygen insertion. I believe that the lifetime of singlet excited oxygen on different solid surfaces ranges from like 1 to about 14 seconds. But even so, that's enough to roam a lot of sites on these grain surfaces and potentially react before de-exciting.
Okay. That's a very long time.
Yeah.
So how long was this first torsional state?
That's a great point. So we actually do, so that's something I didn't actually point out. We do see some fitting, the vibrationally excited state. Yeah, it's about 100 N per centimeter squared.
I see. So do you see also the transitions going like a quick branch of the torsional state, or only as within the torsional state?
So far, we haven't done much of the fitting of this process. So far, it's only been within the specific torsional or the specific vibrationally excited state. We do, however, see, talking about torsion, we see some methyl rotor spreading due to the methyl rotor, but they're just these really, really weak transitions, these B-type transitions that are much weaker in this molecule. So for complete spectroscopic analysis, we do need to continue to analyze though, but because they're these really weak transitions, they didn't really factor into our detection of this molecule, so we haven't gotten to it quite yet.
Are there any far infrared measurements of those torsional?
Not that I know of. Yeah.
Right. If there are no further questions, let's thank Zach again.